Since electric fields and magnetic fields are so similar, we can quickly derive out new equations just by looking at the trends that we learned back in grade 11. All right, for one thing, if you take a look at the force distance graphs, they are identical to each other. After all, they both exhibit this correlation, which is an inverse squared correlation. All right, we've already covered the formulas for both of them, and these are the corresponding formulas, and you can see the similarities between the two. All right. Also, back in grade 11, you would have covered that there's a simplified formula for the force of gravity, which is equal to mass of the smaller object times g. And g is for the gravitational field strength. To figure out the gravitational field strength, we just simply take these guys together, right? So g is equal to g times the mass of the big object over r squared. In the world of electric forces, something very similar happens as well. All right, so there is a simplified formula to describe electric forces where Fe is equal to Q times some sort of constant, except it's not G this time, it is epsilon. All right, some textbooks will use capital E, and that's fine with me. However, the problem is that capital E is often reserved for energy, and at some point we're going to be dealing with energy as well. So just to avoid the confusion, I'm going to stick with curvy E or epsilon. All right, and the derivation for epsilon is very similar to that of a lowercase g, right, where you take k, one of the big charges, and divide it by r squared. And that's what the formula looks like. In fact, I think I have it all animated out. There you go. It's already animated out, and there's that animated out as well. As for the larger object, it will be the mass of the planet. Sometimes it will just be denoted as capital M, and I'm fine with that. All right. As for electric field strengths, there's two types of charges. There's the big charge known as the master charge, and there's the smaller charge which is called the test charge. All right, that's just the grammar that we use in physics. Another thing that we use in the grammar of physics are the units. All right. As for G, the gravitational field strength, it can be described using two different types of unit conventions. All right. You can either describe it as a Newton per kilogram or as a meter per second squared. All right, and you can use them synonymously. And if you're wondering when should you use which one, it really is based upon the question that's given to you. You really want to choose a unit that helps you divide out the units that are repetitive so that you end up with a cleaner unit at the end. All right, so that's how you choose which unit to use. As for electric field strength, yes, it too also has two different synonymous units. You can either measure electric field strength in newtons per coulomb or in volts per meter. All right, and again, the unit you choose is based upon the question that's given to you. You just want to use the one that's appropriate that allows you to divide it out. That's all. Okay, let's just do some case studies of analysis before we move on to calculations. All right, let's say that we have similar charges. All right, and I'm just going to describe it as red positive charge and purple positive charge. What is the field intensity at the exact center? Well, if these two charges are exactly the same, we've covered this earlier, it will net to a value of, that's right, 0. After all, the red charge and the purple charge are equal in intensity, but just opposite in direction, and that's why it nets to a value of 0. Well, we can also observe the intensities outside of the two charges. I'm going to start with the far left-hand side first. Okay, what is the observed E field over here? Well, it's equal to the sum of the red charge and the purple charge. One thing you need to keep in mind is that the purple charge is much further away than the test point, so the intensity of that E field will be much weaker. All right, so if we were to try to calculate out what the intensity is right over here, it's equal to the E field intensity of the stronger red charge because you're closer, plus the weaker purple charge. Let's observe on the right-hand side now. Okay, the E field intensity. That's equal to the red charge, where since it's further away, it's going to be much weaker, plus the much stronger purple intensity charge, all right, because the purple charge is much closer to the test point than the red charge. All right, so that's why it's going to have a larger impact in your E field answer. So I'm making them large and small just to emphasize that this value will be greater than this value. That's all. Well, what if the charges are not similar anymore? All right. Let's say that they are opposite charges, like right over here, a positive charge and a negative charge. Well, with the red charge, its red vector, if you're looking at it right at the center, will be pointing to the right, And as for the blue charge or the negative charge, its vector, as it's negative, will also be pointing towards the right. Remember that positive charges have E fields that emanate away, and negative charges have E fields that point back in. All right, at least that's the convention that we stick with as human beings. So right plus right will give you more to the right. What if we observe to the left of these two charges? Okay, what will this look like here? As for the red charge, yes, the vector will be pointing to the left. As for the blue charge, it is pointing to the right, but remember it's much further away, so I'm going to make it thin just to emphasize that it's going to be a weaker charge. All right, so you have a positive charge moving to the left plus a weaker negative charge moving towards the right. And if you just decide to measure, what the intensity will be right here, you could do that as well. All right, where the intensity of the E field over here will be the vector sum of the blue and the red. The blue will have a vector pointing to the left, and because you're close to it, its intensity will be very strong. As for the positive charge, because it's so far away, it's going to have much less of an impact at the test point. Let's see if this E-field simulator works. I haven't tried it out beforehand. I'm kind of winging it right now. Where is it? Pointer options, back to arrow. There you go. Oh, it still works. Excellent. All right, so if you really want to demonstrate everything and just to see what will happen, here's a positive charge and here's a negative charge, and you can see that the vector sum will be pointing to the right. And depending upon the intensity of these charges, let's say that I decide to double this up, or triple it up, just so you can see it magnified, and here's the corresponding outcome of it. All right, where again the negative charge is so strong that the arrows more or less all point towards it. All right. As for the positive charge, there's a bit of deflection because of the negative charges, E fields that are pointing to the left. And that's why you'll see that this doesn't point up anymore. It points slightly to the right. So I do recommend that you check out this website. All right. What is this called? PhET. All right. So PhET and E fields. Okay, now let's go through some mathematical problems. All right, let's figure out where the E field intensity will be at 0. Now careful, take a look at this. They're not the same charge. This one's at 1 microcoulomb and this one's at 3 microcoulombs. If they were the same, then yes, it would be 0 right at the dead center. However, this guy over here is quite a bit more powerful than this guy over here. So let's go and figure out where the intensity will be at 0. Now intuitively, you would recognize it'll be somewhere over here, right? This guy's weaker and this guy is a lot stronger. All right, so the only way for it to cancel out is to be towards the left of the center of these two. Good. Okay, and now this one isn't complete yet. I think we have to give you one more thing, which is the distance of separation between the two. That will be given to you in the question. All right, so let's say that these two are separated by 100 centimeters. Okay, so we know that the value of 0 will be somewhere over here, all right, somewhere slightly to the left of the center. And now let's create a system of equations to describe all the points, all right, where the distance between point A and point B, we'll just simply call it x. And what about the distance over here? We're not going to create a new variable. Instead, we're going to use what's already given to us. All right, so in this case over here, the distance between here and here is equal to the whole 100 centimeters subtract the value of x. I hope that makes sense. That's equal to 100 centimeters, subtract x. To simplify this problem, first thing we want to do is to create a coordinate system to dictate what are the positive vector directions and what are the negative vector directions, because that will simplify our calculations. All right. So we want to ensure that our E net will go to 0, but that's due to the relationship between these two extremes. All right, so let's take the extreme on the left. That's equal to kq over r, which is x squared. All right, and that's a vector that's pointing towards the right. All right, and we want to add it with k, and then because it's a negative vector, maybe we'll want to put a minus sign over here. It's negative because it's pointing to the left. All right, so this one's positive because that vector is pointing to the right. The second one, the vector is pointing to the left. KQ, I'll just call it C and A, all over r squared. In this case over here, it's 100 centimeters minus x squared. And that's what I've pointed out. Okay, so E net is equal to the sum of these two, but we want our E net to go to 0. So we can take this equation and bring one of the terms over, and then we're just simply equating these two now. Beyond here, you just sub, crunch, and solve. Give you guys 5 seconds to solve for the rest. Did you guys get to the answer of that? Okay, if you need an explanation, let's go through this. All right. First thing I did was I just subbed in all the values, and one thing I noticed is that the K's are the same, so they divide each other out. As for 1 microcoulomb and 3 microcoulombs, if you're wondering, micro is equal to times 10 to the power of times 10 to the power of negative 6. All right, so you could start off with 1 times 10 to the negative 6 and 3 times 10 to the negative 6, but that just takes forever to write down. So the mu's, because there's a mu in each of the terms, you can just simply divide them out. Same as coulombs, they divide each other out as well. So you're left with something rather clean. 1 over x squared is equal to 3 over 1 subtract x squared. All right. From here, you can bring this term up here, and you can bring these terms up here as well. All right. And it'll end up looking something like that. I know it's tempting just to erase the squares, but you can't because there's a 3 here. Technically, yeah, you probably could square root the 3, but that just makes it messier. Instead, how about we just expand and collect like terms, all right, and then simplify. So we've expanded, collect like terms. Notice that we have something that's quadratic, linear, and constant, and in that case over there, we have to use the quadratic formula. Sub the values in, and then you'll eventually find out that RAB is equal to 37 centimeters, and 100 subtract 37 will give you your 63. And that's how you'd work that question out. One last problem to work through before we end off today. How about this case over here? Okay, find out where E net is equal to 0 newtons per coulomb. As we may know, if you take a look at it from the center, well, right plus right will still equal to right, so that can't be the correct solution. So the question is it 0 on the left or 0 on the right? Good, let's think about this first, okay? If we take our test point over here, the 2 Q charge, that's much stronger than this -1 charge. All right, so no way can it ever have a value of 0 on the left-hand side. Meanwhile, on the right-hand side of this mess, you have the -1 Q charge, which is strong because you're nearby, but you have something that's hopefully is just strong enough that'll net to a value of 0 newtons per coulomb, somewhere over here. Okay, and that's how we're going to define our coordinates here. Okay, so somewhere on the right-hand side is going to be equal to 0 newtons per coulomb. Now this question over here, it doesn't tell you the distance between 2Q and -Q, so we'll just call it L. So it's just a relationship between L and X. Okay, use that as your guideline and see if you can get to the correct answer. You want the full answer now? Sure, let's go through the full answer. Oh, cool, I even have a diagram of what's going on over here. All right, so if you were to draw out the diagram, the vector diagram, what it would look like, it would look something like this diagram right over here. Okay, the 2 Q's having a much more overpowering E field than the -Q, where it is possible to have a region over here where the value of the charge, or the value of the E field is at 0 newtons per coulomb. That point can exist. Okay, so now let's go create the equation for this now. Okay, E net is equal to somewhere out here, the positive vector pointing to the right plus the negative vector pointing to the left. The positive vector pointing towards the right is 2Q and is separated by a distance of Lx. Meanwhile, the relationship between here and here is now, you might be wondering, well, why didn't I put that minus sign in here? It's because we created this coordinate system here. All right, so even though it's -1Q, we're really looking at the vector here. Okay, so since the vector's pointing to the left, that's why there's a minus sign here. So it has nothing to do with the -1Q, it has to do with what the vector is behaving like in that point in space. All right, so you just got to be careful with that part over there. So please don't double negate by accident. And yeah, the distance separation is x, and we'll place that as x squared. This E net goes to 0. So now we can equate the two equations, pull out the good old quadratic formula, sub everything in, and we can see that it's just a relationship to L. All right, catch you in the next episode.